Okay, we're going to talk about one of the most important ideas of the entire course. The rest of the way, everything is a building block. It directly connects to the really hard stuff at the end, and so we're going to need it all. So the better you listen to the stories here, the better you're going to do. Hold on, let me make something here. Okay, we saw in the last, before the last test, this is called a probability distribution. It's all the things that can occur, and it's the probabilities at which they occur. So probability distribution. But the problem with this is a discrete situation. So the only things that x could be are 0, 1, 2, 3, and 4, something that's countable, like that we can easily have all the choices. There's not an infinite number of choices. But the problem is that sometimes that isn't the case. What if we were measuring people's heights? We talked about this all the way at the beginning of the course. A height could be, you're not really 6 foot, you're 6.000135. So there's an infinite number of possibilities for how tall you are. So the solution to this is that we're going to turn this into a picture. If, I don't know if you've ever thought about this or thought about this in high school or had this explained to you, but a line has an infinite number of points. So suppose I was interested in x's between 0 and 4. This covers any number between 0 and 4, this line right here. Everything is covered. So here, got it. Here, got it. They're all available. So we solved this problem about the numbers having an infinite number of choices by making a line, or sometimes a curve, called a density curve. But we've got another problem. What are we going to do about how to measure probabilities for this? Well, what we're going to do is we're going to make the area underneath this line or this curve, we're going to make it equal to 1. So we're going to make it all the things that can happen. So the area underneath here is going to be 1. Just like when we summed up these, they always had to be 1 for it to be a valid probability distribution. So all of this area is going to have to be 1. Now, something interesting, and then that makes this become something called a probability density curve. It tells probabilities underneath that line. Now, before we get on to what's really important here, one more side note. If we want to find probabilities in this continuous version, we have to do it as ranges, like between 2 and 3. We could find probability between 2 and 3. We can't do something like the probability of 1 anymore. You say, well, why is that? Well, it's set up that the area is how we define the probability under this thing. And if you look at one single point, okay, the probability of 1 goes up here, and it doesn't have an area. Do you see, this is a height, but if I'm making a rectangle like this, I need the height to have some kind of width. So there are no areas when you just simply have a height, so it won't work. Okay, a couple notes before I move on real quickly here. If this goes from 0 to 4, and this area in here needs to be 1, the probability of anything happening has got to be 1/4. This is a rectangle, so the height times the width has to be equal to 1. It's just the area of a rectangle. So 1/4 times 4 is 1. So that's why this has to be 1/4 to make this a valid probability distribution. Okay, last thing is that this is called a uniform distribution. So the probability is always 1/4 no matter what you pick for x. In a continuous situation, I don't even have any idea where this would happen in the real world, but it makes it very easy to find the probabilities in this situation by using geometry. We're using the idea that area equals the length times the width, or the height times the base, however you want to think of it, to find areas underneath this uniform curve. All right, now this is going to sound silly, but this is the beginning of the most important idea of the whole semester. And the idea is this. So if I were kind of screwing around here and saying, hey, what's this shape? Can you tell me these shapes? You'd get an A in the class if you do. They're poorly drawn, but you know this is a circle, it's a triangle, and this is a square. And you know all kinds of things about these shapes, and they don't stress you out at all. But what about this shape? This is a bell-shaped curve or a normal curve. And what I'm suggesting is that this is just a shape. It's nothing else. It sounds stressful, it sounds like something crazy because it's statistics. It's just a shape. You had these shapes ever since you were a little kid. Your grandma bought you a box, you would shove these shapes into the size of the cutouts of the hole. Maybe you had a mobile. You were playing with these in elementary school. You are totally comfortable with these. You just haven't seen this shape, but it's just a shape. Now, like these shapes, each of these shapes has special properties. There's all kinds of things you know about these. 3 sides, 4 sides, angles are all the same, all kinds of crazy geometry stuff about triangles and circles. Well, this has a special property as well. And the special property is that you can find the proportion, the percentage, the area between any two locations. Those are all synonyms, the same thing, if you know the mean and the standard deviation. So again, if you have the mean and the standard deviation of a normal curve, they can be different sizes. They always have the same shape, but they can be big chubby ones, they can be small ones. But if you know the mean and standard deviation, you can always find the distance between any 2 points. Okay. Now let me show you what that means practically. So suppose, I'm forgetting some things here, sorry. All right, so you say, well, who cares? What's the big deal about being able to find the proportion between any two places? Well, first of all, what if this was one of those probability density curves that I told you about before, and the area underneath here is 1? If that were the case, when you were finding the proportion, what you'd really be finding is a probability between any two places. And that's going to be extremely useful as we move forward. And you go, well, I hear you, but that still doesn't sound very interesting. What do I need this for? Well, this shape happens all over the place. If I were to take all the students out to the front lawn and line everybody up by height, what I'm going to find is this shape. If I were going to take everybody's ACT score and stack them up in order, I'm going to find this shape. My wife is a pediatric physical therapist, and if she were to look at all 5-year-olds in preschool in the state of Ohio, what she's going to find is that there's a mobility score, that their ability would fit on a normal curve. And so what she's looking for is kids who are down here on this end of the curve. And if they're in this low end, this bottom 5% perhaps, those are kids that need developmental assistance. They're developmentally disabled. So now let's finish up with this, what makes this so special, by talking about something called the empirical rule. The mean of this curve is right smack dab in the middle. And we're going to talk about standard deviation steps. It can change on the curve, but here it's 5. So we've got a test. The standard deviation is 5. So here's what happens. If I take one standard deviation step up, I'm now standing at 75. And you take one standard deviation step back, and you're now standing at 65. What's special about this shape is this. Between us is 68% of the entire curve. Always. 68% is between these two locations. Now, let's take another step forward. I take a step, I'm now standing at 80. You're standing at 60. But 60, that's supposed to be a 0. Standing between you and I are now 95% of all the other scores because of the special shape of the normal curve. Now we do it one more time. I'm 3 standard deviation steps away. You're 3 standard deviation steps down. I should say I'm up, you're down. This is 99.7% of all the scores. And so using this idea, you could do some Sherlock Holmes kind of things. So you always know 68 is between 1 up and 1 down. No matter what the mean is, you just take the standard deviation step. 2 steps up and down is 95. 3 up and down is 99.7. So let me leave you with this last thought. Okay, so if I knew that 68% is between 1 up and 1 down, I can find out other things too. So can't you see that if this is 68%, the area that's left over and these two tails would have to be 32%? If all of it's 1, doesn't this have to be 32%? And then this shape is symmetrical. So if you cut this in half, you would get 16%. Well, this one has to be 16, and this one has to be 16. So 16, 68, another 16, that's the whole curve. So this empirical rule not only just tells you about the one up and one down, 2 up and 2 down, 3 up and 3 down, you can also find out some other valuable information because of this rule.